The existence of the cosmic microwave background is one of the two great predictions of the Big Bang cosmology. The other one is the nucleosynthesis of light elements. In the earlier stages of the expansion of the universe, there will be an equilibrium between electrons, positrons, protons, neutrons, and both species of neutrinos, and the reactions would work both ways. And that lasts until temperature drops to about 10 billion degrees, or age of the universe about a second. And simply because the neutrons are a little heavier, there'll be fewer of them in the mix, which is why there will be asymmetry between them and protons. So their mass inequality causes asymmetry because of the beta decay or inverse beta decay reactions that convert one into the other. It requires a little less energy to turn neutron into a proton than the other way around, and so that is the more favored reaction. So after the annihilation of excess positrons, only neutrons can decay. We can again compute the ratio of neutrons and protons using Boltzmann's formula, and indeed initially at very high temperatures there'd be slight asymmetry due to the reasons we just described. But the asymmetry increases as the universe expands, and it finally gets frozen at the value of 0.227 when the universe is only 10 to the 10 degrees hot. So that's how many neutrons come out of the equilibrium, but then they start decaying in beta decay and have a mean lifetime of a little less than 15 minutes. So before they can be combined with protons into helium or other light nuclei, the decay destroys about 25% of them. By the time temperature drops to 1 billion degrees, neutrons and protons can combine to form nuclei of helium, according to these reactions. Some of those newly made nuclei of helium are then dissociated by residual photons, but as the universe expands, they cool enough, and so no more dissociation can occur. So by the time the universe is a little less than 15 minutes old, and the temperature drops to about 300 million Kelvin, all of these ratios are frozen, and those are the abundances that we will observe. Actually, the real network of reactions is a little more complicated, and here it's shown. However, the story we just went through pretty much captures the essence of it. But people who model cosmic nucleosynthesis have to actually do the full-blown reaction network. And the models predict how the abundances of different nuclear species will change in time as all this is going on, as shown here. And you can see that by the time it's all over, say 15 minutes after the Big Bang, the lines remain flat. Except, of course, for small residual number of neutrons that keep decaying. At this point, the neutron-to-proton ratio has dropped to 0.14, and these neutrons end up in the light nuclei that are produced. This is roughly 25% by mass, and this is why there is about 25% by mass of primordial helium. So in this way, the intrinsic mass difference between protons and neutrons, something that comes out of particle physics, determines the abundances of light nuclei created in the Big Bang. Since essentially all neutrons are tied up in helium, its abundance is not dependent on density. But some of the other species do depend on the actual baryonic density. That the reason the reactions don't proceed beyond lithium or beryllium or so is that the universe expands and becomes insufficiently hot and dense to create heavier nuclei. Obviously, the heavier nuclei have higher charges and there is a higher Coulomb barrier to be overcome. So after helium, there is a big gap going to lithium and then also another one going to boron, which is what limits the abundance of those elements. The Big Bang nucleosynthesis predicts abundances of light nuclei. And generally, this is parameterized as the ratio of the number of baryons to photons, which is frozen after all this is complete. Since there is roughly 1 billion photons for every baryon, usually 10 to the 10 are units that are used here. And this ratio is closely related to the baryonic density according to the following simple formula. Since this ratio is preserved after all this is complete, we can measure it today and find out what it was in the early universe. Which leads to the prediction that omega baryons will be of the order of 4%, and that is in an excellent agreement with a completely different argument from microwave background fluctuations. Here are the predictions of the Big Bang nucleosynthesis plotted in one diagram. The different bands correspond to abundances of different nuclei at the end as a function of the baryon density. The steeper the line, the more it's sensitive to the abundance of baryons. And you can see that deuterium would work best as a means of estimating the baryonic density in the universe. Helium-4 does not work at all because the line is essentially flat. The first confirmation of this is through measurement of the helium abundance. Star-forming galaxies are used for this purpose, and since stars synthesize helium as well as heavier elements, that should be in proportion. So by measuring abundance of other elements, say oxygen, and then correlating it with abundance of helium, should be a line that goes through zero if there was no primordial helium created. However, because there was, then the intercept on the y-axis gives you the primordial abundance of helium. And that number, is a little less than 24%, is an excellent agreement with predictions of the Big Bang nucleosynthesis. Remember that deuterium is the most sensitive one to the actual baryonic density. So measuring cosmic abundance of the deuterium before it's processed in stars gives us a means of estimating the baryonic density of the universe. The way this is done is through absorption lines in spectra of quasars. They're hydrogen clouds, so-called Lyman alpha forest, and there'll be Lyman alpha equivalent for the deuterium line because of isotopic shift, its wavelength will be a little shorter than hydrogen Lyman alpha. So the idea is to find clouds where there is enough of material, so the line is already well saturated for hydrogen, but not enough to cover the equivalent absorption from deuterium. And of the order of dozen such systems have been measured, and from the relative abundance of deuterium to hydrogen in these clouds, we can infer the baryonic density. Lithium is a little more complicated because it's also generated in stars, and it's subject to uncertainties of stellar structure and evolution, and so this is why it's not really used to constrain nucleosynthesis. However, we note that its abundance is perfectly consistent with the predictions that satisfy the other measurements like helium and deuterium. And finally, all this also depends on the number of neutrino families, because that they each have degree of freedom in the early universe. And the Big Bang nucleosynthesis predicts that there should be only 3 of them, which is in agreement from what we know from particle physics. Next time, we'll talk about inflation.